Model development through machine learning.
So in this section, we will talk about about the model development, and you will learn about the model development. And we begin by talking about how to design, develop, and implement machine learning models to solve business problems, right? So how do you think you would go about designing, developing, and implementing machine learning models to solve business problems? Any thoughts? See, this whole process of designing, developing, and implementing machine learning models to solve business problem involves a structured process. And let's take a look at the one by one, the various steps that you can take to design, develop, and implement these machine learning models. You need to start by defining the business problem. And there you need to clearly understand the business problem that you aim to solve, and then define the objectives and the key performance indicators that will measure the success of your solution. So you need to outrightly define how would you measure the success of your solution, and that should drive your development of the solution, design development. Second thing that you need to do is to gather relevant data that will be used to train and evaluate your machine learning models, and perform exploratory data analysis to understand the characteristics of data, identify patterns, and validate assumptions, right? Then you need to go about cleaning and pre-processing the data to handle missing values, outliers, and ensure that this is in a suitable format for model training. Then transform categorical variables, perform feature scaling, and address any other data related issues. So that's how you pre-process the data. Then you need to do feature engineering, in which you create new features. Features are the variables that explain, that provide you insights from the raw data, as you see here. So you need to create features or transform existing ones to enhance the predictive power of your models. So the predictive power model is entirely dependent on what are the variables or features that you are bringing into the model. If you miss an important feature or variable, you will not be able to make good predictions. Now, the feature engineering involves selecting, modifying, and creating features that are most relevant to problem at hand. And this comes from your knowledge of the domain, or you need to go to domain experts in this case. Then you need to choose the most appropriate machine learning algorithm based on the nature of the problem. It could be a classification, a regression, or clustering, and also the characteristics of the data. And while doing that, consider factors such as interpretability. How well can you interpret the data? Scalability. Is it applicable for all kinds or scales of data? And the need for real-time prediction. So that's what decides your model selection. Then you need to do the model training, in which you split the data into training and validation sets. Train your machine learning models using the training data. Tune hyperparameters to optimize model performance, and evaluate the model on the validation set to ensure it generally generalizes well on unseen data. It generally does well on the unseen data. And how can you do that? Let's look at, these are the kind of codes, illustrative codes in Python that you can write to do the model training. Come back and take a look at this in greater detail by downloading the PDF file, and keep it for your future reference to refer. Then you need to evaluate the model by assessing the performance of your learning model using appropriate evaluation metrics. Common metrics include accuracy, precision, recall, F1 score, and area under the receiver operating characteristic, ROC curve. Now, what are these? Let's take a look at quickly each of these. Now, the accuracy is defined, as you see here, is being close to the objective target or measure. Now, if you're talking of golf, it could be hole in the golf, or target on the dartboard, or objective truth in the news reporting. Now, it is different from precision, which matters to proximity of repeated attempts, not necessarily near the goal, near the objective target or the golf hole. Examples: in case of golf, ability to get close to hole in one; news reporting, ability to report the truth or as close as possible; archery, ability to hit the bullseye; and exam, ability to get the correct answer on the test. Now, the precision is refers to closeness of two or more measurements to each other, indicating consistency. It does not necessarily mean it is accurate. And examples are: if the digital scale consistently measure a weight of 5 grams every time it's placed on the wall, the scale is precise. Dart throwing: if a player consistently hits the same spot on the dashboard, not necessarily the bullseye, it says he's consistent in his throws. Recall: what is the recall? Little more complex measure. Now, recall is related to what is called true positives and false positive. Now, when you make a prediction, your prediction can be positive versus an actual positive. So you predict right and it is actually right. You can predict positive and actually it could be negative. So that's a false positive. You predict negative and it is actually positive. It is called false negative, and you predict negative and it is actually negative. So these are the true negatives. So let's understand this definition. And then what you see is in your data, how many of these you have, right? And then you define recall as how many relevant items are retrieved, which is how many how many true and false negatives are reported versus the total items retrieved. So if you retrieve 100 data, out of that, how many are true positives and false negatives, which are the relevant elements. What is not relevant is false positive and true negatives, right? And precision is, on the other hand, as you see here, is basically true positives upon the total numbers here. Then let's take a look at, so recall is a true positives divided by the total positives, true positives divided plus false negatives. Then there is something called F1 score, which is a derivation of precision and recall put together in the formula. So just for your knowledge here. And finally, the area under receiver operating characteristic ROC curve is a measure of if it is a perfect classifier or perfect prediction, then the area under curve is maximum. And if it is half-half, it's a poor prediction. And anything more than half-half is called good. And this is plotted on true positive rate on the vertical axis and false positive rate on the horizontal.
Thanks for watching video. Don't forget to like, subscribe, and hit the bell icon for more interesting upcoming videos. See you next time.